Welcome to the DeviceDojo. I'm Joseph, and this is where we tackle the practical side of securing connected devices, from over-the-air updates and fleet management to the broader challenges like incident detection and response, compliance, encryption, and more. Always actionable and hands-on, brought to you by Northern Tech, makers of Mender.io. And let's get started for the first time in 2026. Yes, I did intentionally play the intro music again, just for waking up. Okay, so you can see the year is starting. It's cold outside. It's winter, so I decided to put on my fancy hat. Just for those who do not already know me and the DeviceDojo. So this is a video series produced or sponsored by Northern Tech, who are the makers of Mender, Avaldi, CF Engine, and our business is securing connected devices. If you have any questions, ideas, comments, or rage about what we do, please feel free to kick me personally. The DeviceDojo so far is only this series, but very, very soon I will be adding new content formats such as office hours, live coding, more in-depth dives. The key here is whatever I do, I always want it to be actionable for you to be able to make your connected devices better, more secure. So, what do we talk about today? It might be a little bit strange sounding, but we are going to talk about seccomp-BPF. First, what is the bigger context, how it is actually implemented, how you are going to use it in code, and then, of course, demo and more questions and ranting. So, a typical user space stack in Linux and in probably most other higher level operating systems, let's put it like that, looks roughly like this. You have an application which is sitting on top of everything. Then it calls into library functions. It's very rare that an application goes straight to the kernel. Usually this is abstracted away. At some point, there are the system libraries. The most classic one is libc in many, many cases, and especially in Linux, usually the glibc. And this in turn calls into the kernel for the so-called system calls. So what are system calls actually meant for? Whatever your application does in user space, it is actually somewhat limited. A very, very simple example of what a system call is read. If you're reading from a file, how do you actually realize when there is, or how can you find out where system calls are going on? Well, on Linux, you have two fancy tools. This is strace, which gives the S already stands for system call trace. And if you want a little bit more information, which I usually prefer because I as I already told you, if you are in your application stack, you call into the library and the system call is hidden somewhere far below, then you might want to know at which point you're jumping into the library, from there into the system call, and where all of this goes back. So I usually prefer ltrace for library trace, and with the -s argument, it also gives you the system trace and interleaves this accordingly. I told you read is a nice example for that. And instead of writing a full demo program for this, well, what could be easier than just reading a file and printing it to the screen? And on all of our shells, we have a fancy tool called cat. So we are going to abuse cat here for just reading etc host name and printing it to the shell. If we put all of this through ltrace-s, we get a plethora of logging because there's actually a whole lot going on with such things. But the key point that you can see here is read is a syscall. It goes into the kernel, and it goes back into the library again. write. And what you also can see, this is also important. The first parameter to read or write, for example, is the file descriptor. You might want to memorize this. In the case of read and open, this is number 3, because this is the first free file descriptor on a standard process. So it opens, it obtains file descriptor number 3, it reads from file descriptor number 3, and then it writes to file descriptor number 1, which is a standard output. So it prints to the terminal. Yay, a lot of stuff going on. There are a couple of hundred syscalls by now on standard Linux. And here's a couple of ones which you can, or which you will probably encounter in almost every tool that you ever write or run. Read write, of course, for file interaction. Open close to get the file descriptors. Socket and connect are if you want to do network communication. mmap, memory allocation with file backing very often. Fork is the one which we will be talking about later in a lot of detail, or a lot of detail, some detail, because it actually means you can execute other things. And there's, of course, a whole lot of further management possibilities here. The rule of thumb is whenever something touches hardware, even if it is just storage or RAM or whatever, or needs to do something which is outside the scope of your own application, and this might be the PID, for example, because this is only visible to the operating system, technically, then it is a syscall at some point in time. And as Michael points out, syscalls have a lot of other cool features. They can also finally solve Schrödinger's riddle, because it can tell you if the cat is actually alive. That's a very good one. I need to remember this one. So the key point is that many of those system calls expose system critical features. If you are allowed to get into the syscall and do something weird, then you are probably quickly able to compromise the full system, which is obviously not what we want. In kernel, how can we deal with this? There's a couple of things, but the logic might be complicated. And how can the kernel know which system calls you actually want to deal with? Yeah. And here, a very weird feature, or weird feeling feature, comes to the rescue. It's called eBPF. eBPF stands for Extended Berkeley Packet Filter, and it actually originates as a firewall technology. So Berkeley Packet Filter basically is a firewall technology, or yeah, let's call it firewall technology, because you can define which packets to drop, which to forward, whatever. And eBPF evolved into an in-kernel virtual machine with some very restricted logic about how the code can be, which runs on this virtual machine, can be compiled, which restrictions it has, how its runtime needs to be defined. The very important part here is that there cannot be indefinitely long running eBPF programs. So as far as I understand it, all of the tool chains make sure that they have a definite flow of run, and that they also end. The main use case, and why a lot of companies, and especially non-embedded companies, threw a lot of money onto eBPF, is obviously networking. And here it is XDP, the extreme data path. So this is logic implemented in eBPF, which enables the firewall logic. Let's stick with it, to process a much larger number of packets on commodity hardware than you would be able to if you need the full networking stack. And this obviously is very important if you are running data centers or services, so because then you can just save on money. So not surprising, the big companies behind this, for example, are Google, Meta, Facebook, Netflix, all of those. The one part where things fall together for us is that eBPF is event triggered. In the original use case, this was when a packet arrives. In our use case, it is when a system call is entered. The good part is that people have seen this potential and have added those events as hooks to eBPF. So you can by now use it for tracing, for all kinds of security inspection, for analytics. And yay, obviously, is this what we're going to do? Yes, somebody did just say security and events. There has been this thing called seccomp, short for secure computing, in Linux for a long time, even before BPF. But it was very, very restricted because you would start your process. You would say, hey, these are the file descriptors that I need. I'm done with my setup. Now I enter seccomp state, and whatever tries to break out of this must obviously be an attack, and I'm out of here. Therefore, if somebody manages to attack your application and seccomp is enabled, the application would just segfault essentially or be terminated, and you get a descriptive answer that something bad was happening in there. The problem is that seccomp, or not exactly a problem, you need to make the kernel aware of this. Config seccomp is by now enabled on almost all the default Linux kernels. But it again, I find it kind of funny. It again is in itself a syscall interface, and because its features are so limited, it really is just like, yeah, this process now is on seccomp. It is really coarse in control and cumbersome to use. And now everything falls together because yes, eBPF can help here. If we add seccomp, then we can also add seccomp filter. And this means seccomp does not only say, hey, this process is on seccomp, I'm going to blow up now. No, you can define, hey, if this process calls into the kernel, which call is it? Is this one allowed or not? What are the rules? Do I just have to log it? Do I have to go boom? Whatever. This is a logic implemented in eBPF. So this now would sound like, okay, so I need to use the syscall to set up seccomp, and then I even need to write eBPF code, blah, blah, blah. Nope. And here, the final part, seccomp provides a very convenient user interface for this. And this is available on literally all Linux platforms by now, even very embedded ones. It's easy to be added. And this is not exactly new or bleeding edge or whatever. This is super standard technology by now. It is used in Android. It is used in the Chromium browser. It is used literally everywhere where your processes have to deal with possibly malicious user input or data from third sources. So super easy to add. Because this is how it works. You include seccomp, you get a filter context, and then you say, hey, to this context, here are my rules. I want to blow up on this, I want to blow up on this, I want to blow up on this. Usually you select a number of syscalls that do not make sense for your application. For example, if you're a network process, which does just answer incoming API calls, you probably don't need to fork, or you do not have to open new files, things like those. So you can and should block those calls. Vice versa, if you're on a logging application, well, you probably do not need to open network interfaces. Again, block those. you can see here, the rule that I'm adding is the cannonball one, kill process, obviously, if the system call execd is being called. So whenever now something after this call in the process tries to call for execv, it will be terminated, and I'm gonna get a nice crash log. The interesting part, obviously, is, or what you have to remember, that you cannot unseccomp, because that would be kind of hilarious. You say, no, I want to block on this and this and this, but oh, I made up my mind. And I now want to be exploitable again. No, this doesn't work. So whenever you edit stuff, it stays there. The only thing that you can do is to gracefully shut down and reset up the process on the next iteration. I told you, you get a nice syslog. So here's an example. If something would now happen in your application, which tries to end up, oops, I should not click on the slide so quickly, which tries to execute a shell, for example, because this is usually the first thing that an attacker does. Then K-Audit would say, hey, no, this isn't going anywhere, and it kills your process, not with the sec fault, but with a bad system call. And if your system is configured for it, you get the core dump. And this is obviously what we're going to demo now. You already saw this, my famous boom. Did I even mention that I have sounds now? Okay, demo. Let me get my screen. So remove this. Give me that. Here we are. As already mentioned, a very simple trace, just for clarification, is very, very long. You see, cat etc host name QIJ x2 looks like this. We can scroll up a little bit. It's 160 lines. If you're interested, here is the read, the one that we are actually looking for. But there's a lot of stuff going on, like locales are being loaded, maps, all of the libraries that are required go through LDSO preload, and. You see, this is occasionally helpful, but in most cases, better for just understanding. So I have this demo application already. Let's just look at the code for a little bit, because I found it quite... nope, wrong terminal. I think here it is. Recipes, demo, seccomp. Yep. In a little bit more detail here, I get the library, seccomp page, and here is a somewhat lengthy declaration of the stuff that I want to filter on. Exec, fork, before clone, ptrace. Ptrace is another interesting one, because if your attack cannot fork, it might still try to attach to another process for extraction of secrets, or dealing or tinkering with the other process. And the demo application literally just does a trivial HTTP get to some other public endpoint. And I'm simulating here that if there was, where is it? Still one down here. If there was a malicious payload in the response, it could now try to open the shell. And hopefully the seccomp will prevent this. adding this to a Yocto build, because this is obviously what I do all the time, is also very straightforward because it really just needs seccomp, which, as I promised, is available, and extending the kernel configuration is what I told you. Enable seccomp. Okay, so here we go. Run QEMU, no graphic, slurp. Gonna log in. So this is my application. If it works as expected, it enables the filters. It calls some endpoint. It prints the response. Yay. So now, if something wrong would be happening, boom. I love that. The response arrives, and here would be obviously the entry point for an attack. But yay, K-audit says, nope, this is not allowed. You are not able to do the execv syscall, and you're aborted. Cross demo, obviously, if seccomp is not enabled in this process, this is not a general flag. This is something in the demo application, by the way. Then it would just pass out, and yay, have the inherited privileges, which are root in this case. So probably have your system compromised at this point, which is not what you want. As promised, I have the full source code already published on the Mender Hub, with all of the lengthy listing with the explanations and all of this stuff. If you want to know a little bit more about how seccomp works internally, then I would suggest to actually look at the kernel documentation itself, because I feel that this is quite well documented. What is left for us to talk about? I always suggest to make Unix philosophy-ish single binaries. So instead of having a big monolithic block, which needs to take care of everything, like logging, network access, possibly even configuration management, your payload, whatever, then obviously this process needs to run as root and needs to have access to all of the syscalls. Split your application stack into a networking part, into a logging process, into a control process. And by adding seccomp-BPF, you can easily say, okay, this one, and usually it's the networking one, but we'll get to that in a second, should be reined into just networking and nothing else. The obvious big caveat is this usually just applies to classic C, C++, because the standard attack path for such is a buffer overflow. That usually does not exist in Rust or Go or similar languages unless you actively enable it, which is stupid in most cases. But still, there is a lot of C and C++ code out there, possibly in your libraries that you're indirectly using from Rust or Go, because you're still linking against stuff, obviously. And there are still a lot of other attack vectors. So, because networking is the most obvious way where you get where you receive bad data, but the bad data might also come in through a crafted configuration file, for example. If you have your system all locked down, but people can come along, bring their thumb drive with personal settings or whatever, who says that the parser for the settings is actually fine and not crashing on malicious data where they just found a breach? So consider this for essentially each and every process which deals with input data that is not necessarily and properly sanitized. And this is where I haven't seen this for real yet, but it might be there. This can also happen on Rust or Go. If your data is crafted such that it can coerce the algorithm into a different path than you anticipated, then it is not exactly a Stack Overflow, more like a logic flaw, but it could still go to a syscall. So it's obviously not as important there, but keep in mind that syscall sanitation is always a good idea. With that, I would say that's mostly it for today, unless somebody has remarks or questions. As already pointed out, here's the full tutorial link explanation with everything that you need to reproduce this on Yocto. And the next time, on February 12th, we're going to talk about something a bit similar. It's also about making sure that your code doesn't go boom if you deal with bad data. But in that case, we're talking about something that is entirely in user space, and that does not only apply to Linux, but also to Zephyr, for example, and literally everything which has a sufficiently powered libc underneath. Yeah. And then I'd say that's it for today's DeviceDojo. Obviously, hit subscribe somewhere down there on YouTube, or follow Northern Tech and me on LinkedIn. Drop comments if you've got questions about what we covered, ideas, future episodes, whatever. I'd love to hear from you. If you're ready for professional OTA updates in your own projects, of course, check out Mentor.io, the sponsors of this whole thing that we're doing here. The links are in the description, and hope to see you in the next episode. Oh, and one thing, I almost forgot it. FOSDEM is coming up. So if you're seeing this earlier than FOSDEM, make sure to say hello there. Right? Okay. Bye, folks.